Welcome to the Explainer. Okay, let's dive right into this, because today we're doing something a little bit different. We aren't just looking at numbers on a page, we are looking at the hidden code of reality itself. I want you to think of statistics not as some dry, boring math subject you're forced to take, but as a cipher. Listen, for those of you tackling the Cambridge 0580 mathematics syllabus, mastering graphs and charts is exactly like learning to read the matrix. There is no paper, only patterns. Learn to see the code behind every question, and suddenly all that raw, chaotic data around you organizes into crystal clear insights. In this explainer, we are going to decode that matrix together.
Now, to really understand the power of this code, we have to look at the stakes. And historically speaking, the stakes have been incredibly high. Statistics have literally shaped human history. Just look back at the 9th century. The Arab philosopher Al-Kindi used early statistical methods to decipher encrypted cryptographic messages. He was literally cracking codes. Fast forward a bit to the 14th century, and you've got Italian banker Giovanni Villani using statistics to track the massive, complex commerce of Florence, basically organizing the economic reality of an entire city. But honestly, the most striking example is Florence Nightingale in the 19th century. During the Crimean War, she used statistical data to prove that soldiers weren't actually primarily dying from their battle injuries. No, they were dying from preventable illnesses like cholera. By decoding that data and presenting it visually, she completely changed sanitary conditions and saved countless lives. So yeah, that is the raw power of the tools we're about to learn. It's not just math, it's a way to see the truth.
So, how exactly do we harness this power for your exams? Well, we're going to unlock 6 distinct levels of data mastery today. 1. Discrete versus continuous data. 2. Displaying simple data. 3. Grouped frequencies. 4. The geometry of data. 5. Fair data comparisons. And finally, number 6, tracking changes over time. Let's get into it.
Level 1. Discrete versus continuous data. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, so this right here, this is your red pill, blue pill moment in data reality. Before you can graph absolutely anything, you have to know what kind of data you're actually looking at. It's the foundational rule. If you get this wrong, every single chart you draw after this point will be fundamentally flawed. There's a very clear dividing line between how we measure the world. On the left side, we have discrete data. These are specific, unbreakable values. Think about a dice score, right? You can roll a 3, or you can roll a 4, but there is absolutely no universe where you roll a 3.72. Your house number, the number of tickets sold for a concert, these are discrete. They are distinct, separate items. On the right side, though, we have continuous data. Now, this can be absolutely any value within a range, limited only by the accuracy of your measuring tool. If you run a 100-meter sprint, your time might be recorded as 13.8 seconds, but if you have a better stopwatch, maybe it's 13.76 seconds. With high-tech lasers, 13.764 seconds. Things like height, weight, the speed of a moving train, these flow continuously. They don't jump from one whole number to the next, they glide.
Level 2. Displaying simple data correctly. Once you've successfully identified your data type, you need to choose the right visual weapon to display it. Let's start with the most basic tools designed for simple, discrete data. Enter the standard bar chart. Here on this slide, we are looking at the frequency of chocolate buttons found in 20 different packets. 4 of those packets had exactly 35 buttons, 7 had 36, and so on. Now, the absolutely crucial point I want you to see is right here. In a standard bar chart, the height of the bar represents the frequency. That's standard. But look closely at the visual design. The bars strictly do not touch. Why is that? Well, because the data is discrete. A packet has 36 buttons or it has 37 buttons. You're never going to open a packet and find exactly 36.5 chocolate buttons, right? So we intentionally leave a physical gap on the chart to show that separation in the real-world values. It's a visual cue that the data cannot exist in the space between.
But what happens when we switch over to a frequency histogram? Suddenly, the rules of the matrix change entirely. For a histogram, the bars absolutely must touch, they have to be of equal width, and the value is written right in the middle of the bar. Let's use British shoe sizes as an example here. Now, you might intuitively think a shoe size of 7 is completely discrete, right? It's just a 7. But think about the reality of human feet. A student with a foot size ranging anywhere from 6.75 all the way up to 7.25 is going to round that measurement to fit into a size 7 shoe. Because there's this underlying continuous scale of foot length happening behind the scenes, the bars on our histogram have to touch.
That touching represents the continuous flow of real-world measurements being grouped into distinct categories. It's a really subtle difference, but examiners love to test you on it.
Level 3. Organizing grouped frequencies. So what happens when your data set is just way too massive? If you're tracking the finishing times of hundreds of marathon runners, listing every individual number becomes completely useless, and grouping the data becomes absolutely essential. Time, as we know, is continuous data. We can't list every single microsecond a runner crossed the finish line, so we create groups. And this chart brilliantly illustrates how we use mathematical inequalities to do this flawlessly. Look really closely at the first group here. 2 hours and 5 minutes is strictly less than t, which is less than or equal to 2 hours and 10 minutes. The upper bound is precisely 2/1000, and the lower bound is 2/0500. By using the less than or equal to sign on the upper bound and the strictly less than sign on the lower bound, we ensure there is zero overlap. Think about it. If a runner finishes at exactly the 2/1000 mark, they fall neatly into that first group, not the second one, because the second group requires a time greater than 2/1000. It's a perfect airtight sorting system that ensures no data point gets counted twice or left behind.
Level 4. The geometry of data. Pie charts. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's shift gears from rectangles and straight lines over to circles. Pie charts aren't just pretty pictures to make a report look nice. They are highly rigorous mathematical tools used for displaying relative sizes. To build a perfect pie chart and get full marks on your exam, you have to follow a very simple 3-step algorithm. First, you need to calculate the relative frequency. That's just your specific frequency for that category divided by the total number of data points. Second, because we all know a full circle is precisely 360 degrees, you take that fraction you just calculated and multiply it by 360. This locks in your exact angle. Finally, step 3, you take your trusty protractor and actually draw that resulting angle. It's an amazing process, really. It converts raw, seemingly random numbers into perfectly scaled geometry.
Let's actually see this in action with a football team's season record. We'll just call them Team A. Let's say they played 40 matches in a season. Look at this chart. Notice how one single section visually dominates absolutely everything else. In 22 out of their 40 matches, Team A scored 0 goals. Ouch. But following our formula, 22 divided by 40 multiplied by 360 gives us exactly 198 degrees. That's 55% of their entire season represented by that massive, dark, scoreless slice. A pie chart takes that grim offensive reality and makes it completely impossible to ignore. You don't even need to read the numbers to know they had a rough season. The geometry tells the story instantly.
Level 5. Making fair data comparisons.
But here's where things get really interesting. What if we need to compare Team A to another team? This right here is where so many people fail to read the matrix properly and fall into examiner traps. When comparing Team A and Team B using percentage data derived from a composite bar chart, you really have to look closely at the numbers. We already know Team A scores 0 goals 55% of the time. But look at Team B. They only have scoreless games 20% of the time. Furthermore, Team B is scoring 3 or more goals in a massive 25% of their matches compared to Team A's measly 10%. Just taking in these numbers at face value, you'd immediately conclude that Team B is having a vastly better season, right? They seem like an absolute offensive powerhouse compared to Team A.
But hold on just a second. There is a massive statistical trap hidden here, and it's exactly the kind of thing Cambridge 0580 tests you on. The data only displays the number of goals scored and completely fails to show the number of goals conceded. Our brilliant conclusion about Team B being superior was completely flawed because we had a massive blind spot. Yes, Team B might be scoring tons of goals, but what if their defense is absolutely terrible? What if they're letting in 5 goals every single match and losing every game? We simply don't know. And that's the lesson. Data is just as much about what isn't shown as what is shown. Never, ever draw sweeping conclusions that go beyond what the specific limits of the data allow. See the whole board.
Level 6. Tracking changes over time.
So, when we have continuous data sets that evolve and change, we need the ultimate analytical tool in our arsenal, the line graph. Now, line graphs aren't just for looking backward at what already happened. They actually allow us to fill in the blanks of reality. The challenge for you becomes, can we predict a data point, Let's say the exact temperature at 10 a.m., even if we never actually recorded it in the real world.
Let's look at this. With these temperature readings taken in New York, we have data at midnight, 4 a.m., 8 a.m., noon, and 4 p.m. Notice the massive 4-hour gaps between our recorded points. We have the temperature at 8 a.m. and we have it at 12 p.m., but 10 a.m. is completely missing from our data table. Now, if this were discrete data, like the chocolate buttons, we'd be totally out of luck. You can't guess what's in the gaps.
But time and temperature are continuous. They flow. And the mathematical key to solving this mystery is something called the valid assumption. In statistics, when plotting a line graph over time, it is mathematically acceptable to assume that the variable, in this specific case, the temperature, changes at a constant rate between the actual physical readings. Because of this accepted rule, we can literally draw straight lines connecting our dots on a graph. So to find the unrecorded 10 a.m. temperature, we simply go to 10 on our horizontal time axis, draw a line straight up until it hits our graph line, and then read straight across to the vertical temperature axis. Boom! We've successfully decoded the blank spaces. We've seen the pattern where there was no paper.
And that brings us to the end of our explainer. From Florence Nightingale using data to save lives to predicting the weather hidden in the gaps, you've seen how mastering these rules transforms raw, scattered numbers into undeniable truth. You now know the crucial difference between discrete and continuous data, exactly when your bars should touch and when they shouldn't, and how to spot a dangerous trap in composite data comparisons. Statistics truly is the code of reality. The only question left is, armed with this framework, what will you decode next? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep observing, keep questioning, and I'll catch you next time.